Hello, and welcome to this MCA webinar on understanding integrated components and what they can do for you. My name is Carrie Hitchner, and I'm the Marketing Manager for the Motion Control Association. This webinar will be recorded, and a link will be sent to you within the next 24 hours. If you have any questions, please submit them in the questions panel of your webinar screen, and we will answer all questions via email after the webinar has concluded. I'd now like to introduce our presenter for today's webinar, Kristen Lewatsky. Kristen is a contributing editor for Motion Control Online and has written about motion control and automation for more than 8 years. As a technical writer, she covers a variety of subjects, ranging from memory and microelectronics to nanotechnology, lasers, and photonics. Kristen previously worked as an engineer on NASA's Chandra X-ray telescope before switching to writing about technology. Kristen holds a BS in physics and a master's in optics/photonics from the University of Central Florida. And now I'd like to thank our sponsor today, Micro-E-Systems, for supporting this webinar. Micro-E-Systems is a member of the GSI Group, a publicly traded worldwide manufacturer of enabling technology products and systems. Founded in 1994 to develop the world's most innovative miniature optical encoder technologies, Micro-E-Systems products have been used by thousands of companies worldwide to solve a wide range of motion control applications. Our advanced miniature encoder technology and application expertise has driven innovations in the design of machinery, equipment, and instrumentation in many industries, including medical, life sciences, industrial robotics, automation, metrology, semiconductor manufacturing, packaging equipment, entertainment, energy, military, and scientific research. Now I'd like to hand it over to Kristen to begin today's presentation. Kristen, you can go ahead and take it away.
Thanks, Carrie, and also thank you to the sponsor, Micro-E, for making the webcast possible, and of course, thank you to everybody out there who's attending. Let's see, so integrated components. I thought it was a good time to kind of take a look at not just what's going on in the component sphere, but kind of the larger issue of integration, because there's some really exciting stuff going on at the systems level and tools that are available today that might really surprise you. So in fact, that's one of the things I really enjoy about covering technology for a living, is getting to see things go from kind of the lab level and the intro level to broad acceptance. When I kind of started covering the industry a while back, servo motors were even potentially a hard sell for some industries that were kind of scared of all that wonky electrical stuff, let alone something complicated like integrated components, or at least that's how they viewed it. But you know, you fast forward to today, and number one, motion control is broadly accepted, you know, across a wide swath of industries, because that's how companies stay competitive. But also, integrated components are really starting to crop up all over the place. So let's kind of take a closer look. First, kind of underpinning anything that's going on in integration right now is obviously the integrated components, and you've got a slew of them. You've got drives out there now. They can not just hand down commutation commands, they can perform path planning. You've got encoders that can operate in master-slave configurations. You've got motors that integrate drives, they integrate encoders, and all of those, sometimes they sort of think of it as a giant Venn diagram where every component in the system is trying to take functionality from the others. But when they're kind of properly integrated together, you get highly functional, really simple systems, and also for reasonable prices. Carrie, if you can go to the next, please. So kind of the standard wrap on these smart components and integrated components, easier to put them together. You've got processing power and memory on board, and part of the benefit there is you can kind of leverage economies of scale from consumer electronics that helps drive down the cost. You also potentially have fewer points of failure if you've got fewer components in the system. And some of them even integrate safety, self-tuning. A lot of ways to make life easier, especially for people who are doing systems that aren't necessarily hardcore machine builders and so on. If you've got people whose value prop is something else and they need to get objects from place to place, the integrated components are really great for that. Let's see, next one, please. So the model that we've had for quite a while from the communication standpoint, and that's kind of what's making this integration revolution that's underway, is kind of what's fueling it. In the past, we've sort of had two separate worlds that, if at all, did they speak to one another. You had the control network on the machine, and that was your drives and your motors communicating, your encoders communicating, controllers, and that pretty much stayed on the machine. And then you had your information and communications network, and that was something where you could export data from the machine and use it in that network, but it had to be sort of consciously done, sometimes in batch modes. Same thing with operational data. You didn't really have an easy way to get that out. Those things were kept separately. I remember especially at the beginning talking to a lot of people who said, I can't get my end users to agree to connect their line up to the internet because they're afraid about security. As well they should be, but there are so many levels of security in place these days, and the trade-off for having that connection is being able to get remote support, to be able to do easy firmware upgrades. I talked one time with an integrator who described doing a firmware update from his laptop as he was walking down the jetway to a plane. So there's a lot of benefit to be had for connecting your system to the network. But the way it's always been is, no, you want to keep them safe, you want to keep them separate. But increasingly, there's huge benefit to be had from combining them, and that's kind of what's going on right now, onward and upward. So we kind of have two flows going on right now, and that's, on one hand, you've got intelligence moving down into the components, and that's been going on for a while. Carrie, could you get me to the next slide, please? That's been going on for a while. It started at the plant level, and you had intelligence at the machine level with your controller and your I/O. And as time's gone on, we've been getting more and more intelligence at the component level, not just with processing power and memory, but you're also adding sensors, you're adding diagnostics, and the question then is, now that we're getting the ability to get all that information, what do we do with it? Next slide, please. Well, the other flow that's going on right now is information is moving out from the component level upward, so that initially it was pretty common to have the machine being able to leverage data from the components, but now you've got communication within the line. You've got shop floor to top floor happening from the line to the plant, and that kind of stuff can also be put in play with your ERP system and so on. So it's the information flowing around that's really enabling some of these things we're going to be talking about. Next slide. So kind of the chapter and verse of integrated components back when I was first talking about them was, it's a good thing, like, again, you have your motor drive or your encoder integrated in your motor. You've got fewer cables stringing around. You're not running a cable from the motor to the cabinet. That means you don't have things flexing. You've got fewer points of failure. You also don't have to pay for the cost if you're able to either have these integrated components hanging out on the system or at least having them in closer proximity. Obviously, it also, as we talked about earlier, simplifies your system because now some of these other components can do things like your path planning. But the downside was, they really weren't good at synchronized motion. They could do a couple of axes, point to point. I mean, even a PLC could run a couple of axes of point to point type motion. But if you wanted to do something crazy like draw a circle, it was really hard to do that with some of the earlier integrated components. But time heals all. And now what's going on is you've got network smart motor drives, and they can do synchronized motion because they're linked up. Even if it's not going outside the plant, you've got Ethernet running on a lot of these machines, which is great for a number of reasons, actually. Among other things, you can plug into an Ethernet port anywhere on the machine and get to anything on the machine, so there's less of the crawling underneath to get to an I/O port, which I think makes a lot of people happy that I've talked to. But it also allows these individual components to communicate on the millisecond level. Now, depending who you talk to about your various flavors of Ethernet, industrial Ethernet out there, granted, you do have some issues of determinism, but the question is, for the kinds of moves that need to be made, how deterministic does it need to be that people, the experts that I've dealt with, it's totally deterministic enough for the time windows and the motions that need to be made on these systems. And even if you're talking about a packaging line that's running at 300 parts a minute, you can still get there with Ethernet, so it can do the job. Next slide. So let's see, as far as integrated motors go, again, we're talking about things like having the drive on the motor or the encoder on the motor. One new trend that I'm starting to hear a lot of muttering about is trying to come up with a single cable solution for power and feedback. And that's something that, again, that minimizes your cables. And that's important, as you probably all know. Single biggest point of failure is your cabling, because you get a lot of flexing, a lot of opportunity for damage. Things get, tripped over and yanked on by forklifts and all that. So the less of that you got going on, the better. Having the motor on the machine, depending on who you talk to, that can cut your need for cabinet space by as much as 70%. You can cut your energy costs by about 30%. And if you think about it, I mean, what are the things, especially on the factory floor, that are in shortest supply? It's usually space, it's power, and it's air, slash cooling. So these integrated systems can really address all of those issues. And then at the same time, depending on the integrated motors, if you've got it integrated properly into your system as a whole and you're doing it over a shared power bus, then you're looking at being able to do regen. And that's really great because you can go ahead and be able to, number one, share power. Number two, if you've got a capacitor bank, you can store power momentarily. But the other part of it is depending on the power conditions where your factory or facility is located. There are power companies out there that will go ahead and set quarterly power fees by peak demand. And in a case like that, being able to minimize that peak demand by using regen is actually pretty huge. I mean, that can make a big difference in the bottom line as far as the operating costs. So all good things. Next slide, please. And of course, everything's getting smarter out there. So let's now take a look at having all of this intelligence in the components, what that's actually doing, not just from the point of view that we just talked about, but kind of from a larger system level and functional level. So first of all, it definitely simplifies design. You've got mechatronics going on out there, which I sort of rolled my eyes at the first time I heard about it because it just sounded like a buzzword, but it really is sort of a distinct discipline that involves doing a lot of modeling and analysis and so on, so that, you know, the old model of machine building used to be, hey, you know, I'll come up with kind of a general design in the mechanical guys, and we'll punt that over to the EE guys and say, hey, hang some motors on it, and then they'll hand it over to the control engineers and say, you know, work your magic, make it work. Nobody really talked very much, a lot of finger pointing, and the bigger issue was, you know, you built the machine according to calculations, but once it was up and running and you started operations, all of a sudden all those lovely resonant frequencies started showing up, and you had vibration modes happening, and the only thing you could do is mechanically damp it after the fact. Well, mechatronics lets you do something entirely different. You can come in and do the modeling to figure out ahead of time what your resonant modes are going to be and try to work around them so you don't run into these problems ahead of time. And you know, it's not just being able to design at that level, but there are also all kinds of tools out there now, a lot of online shopping, a lot of vendors have got software packages that you can use to help you choose exactly the right motor for your application, take into account things like power factor, inertia, load matching, all of that sort of stuff, so that you can wind up with the right component. I used to laugh because a lot of what I talk to people about is kind of, you know, design rule of thumb used to be, well, you know, let's look at what we used on the last design and add in a fudge factor of about 20%. That'll make sure that, you know, we get to where we need to go. And that's great, except when you look at it, you know, 3 or 4 generations on, what you've got is this kind of giant whispering gallery where there's 20% added to 20% added to 20%. And all of a sudden, you've got a motor that's wildly oversized for the application. You're spending a lot more money than you need to be spending to get the job done. And that's where some of these sizing tools are really worthwhile, because they kind of help you figure out exactly what you need to get things done. That being said, there's also, you know, an important caveat here, which is you have to design for a realistic situation. If you've got a high reliability application, then you want to make sure that you've got spares in-house in case something ever goes south. So if you've got, you know, 100 axes and 25 different motors, that's a lot of money to put into spares sitting around on the shelves in the eventuality of, gosh, we're going to need one. So obviously you want to be also thinking in terms of trying to kind of keep it to a smaller subset, you know, within the bounds. Maybe the important axes are the ones where you use the, you know, exact motors that come up out of these sizing programs, but just, you know, something to keep in mind. And the thing I think about is antivirus programs. You know, more isn't always better. You can have 3 or 4 antivirus programs and you're going to be absolutely riddled with problems. So sometimes just enough is more what you want. Oh, and the other thing is, yeah, the more memory, the more processors that you have as far as the smart components, that is kind of where you need to keep an overall handle on the system level design, because the more you have packed in close together, the more heat they generate. They're going to generate a little bit more than they would if you weren't adding all the electronics. So just something to keep in mind. Next slide, please. Yep, so intelligence in the system gives you a lot more design freedom. So it all is a good thing. So let's see, next slide. So next level that integration can work for you on is maintenance. Kind of the way people used to think about it if they were good. So if they were bad, they lurched from failure to failure and kind of did what they had to do to keep things up. And in some ways, that really winds up being a significant problem, because what can happen is, the line goes down, and depending on your industry, you're talking thousands or hundreds of thousands of dollars an hour for downtime. So great, maintenance goes flying out. They swap out everything inside the motor and the encoder and the drive and whatever it takes to get things out, the cabling, and so on. What I hear a lot from vendors is they get a pile of stuff sent back to them saying, hey, there was a problem, and it's perfectly good components, because the maintenance people are just desperate to get the line back up. They're swapping out everything, and they don't really have any way of knowing exactly what is what, and no opportunity to really test it. So in a lot of cases, they're swapping out good parts just in the effort of getting things done. More organized companies have, scheduled maintenance set up. Maybe it's monthly, maybe it's quarterly. If they're really organized, they're replacing parts at specified intervals that they've determined over time, statistically, and so on. Maybe they're trying to do their preventive maintenance. Maybe they're not. A lot of times there's so much that needs to be done during that scheduled downtime that there's not time for silly things like lubrication, which is what leads to more downtime. So anyway, that's not necessarily the most effective approach. That's where integration can help us. Next slide. So the thing that integration can do for you is now you can go from reactive to being proactive. You can go ahead and add data from those sensors we talked about, add that to your model so that you can get a better fix on what's going on. You can have use accelerometers that are going to give you vibration frequency. You can look for variation that indicates you've got bearing issues. You can look at current sensors indicating that your drive is drawing more than it ought to be, or that your motor's running extra hot. A lot of information in there. It can be part of some of these models that I was talking about earlier, and definitely improve your ability for uptime. But you can even do more if you take it to the next level. Next slide, please. And that is when you don't just use the real sensors, but you can actually do virtual sensors in a way, because the encoder feedback and the encoders in direct connection with the drive, the encoder can help reveal vibration modes. So one of the things that you can do if you've got your system integrated together, and if you've got a way to access that easily, then you can go ahead, do an analysis on your output, and you can find out what's going on frequency-wise. Are you seeing something that indicates that you might have bearing wear or something like that? You can get a better fix so that if your system is having trouble, you know you need to get out there and tune it now, because sooner or later that is going to give you bearing failure. So now you're moving away from this, I'm going to replace everything when the machine shuts down, or I'm going to replace everything on a schedule, whether it needs it or not. Now you're replacing when you need to replace. You're keeping an eye on it all the time to see whether there are any issues that are going to cause problems, so that you're less likely. You can never say never, but you're much less likely to wind up with unplanned downtime because you can kind of see things coming. And this kind of network system that I'm talking about, it's not like it's something where you're checking in once a month or once a week or once a day. This is a real-time ongoing thing, so that at any point when your system starts to have problems, bang, you know about it. And you can have sensors, or not sensors, limits, software looking for limits. Anytime you go outside of those limits, you get an alarm, maintenance is down there, and bang, you're all set. Or you can set it up for the next time there's a shutdown, and you're doing it with enough notice, and you also know that whatever you're replacing really needs to be replaced. Let's see, and also, actually, no, we'll talk about this later. So anyway, onward and upward, next slide. So integration also pays big dividends for safety. The old way, you had relays, you had e-stops, you had light curtains, you had doors, a lot of mechanical stuff that would make the whole machine have to shut down for a lot of activities. Kind of makes it hard to, obviously you want to keep people safe, but you also want to keep producing. How do you ensure both of those things? And the old way was not as effective as it could have been. So next slide. So now you've got integrated safety. You've got system-wide safety PLCs that do nothing but keep track of what's going on with your system. I'm blanking on the standard name, but you've got your standard safety modes. You can do safe speed, safe torque off, safe direction, and that allows you to do things like use your motors to clear jams, do things like cleaning. I was just talking with somebody back in August for the productivity article, and they were mentioning a company that was able to cut the cleaning time for some rollers by, I believe, almost 50%, because they were able to use safe direction, and instead of having to, every shift, clean a little bit and then jog the machine, and clean a little bit and jog the machine, and jogging it required getting out of the enclosure, shutting everything down, restarting the machine, and then moving it, shutting the machine back down, opening the enclosure. And it took them something like 45 minutes to do this. By having safe direction and safe speed, they were able to do it continuously. So that's actually huge. Another thing that this kind of intelligent and line-wide safety gets you is you can do zone safety, so that you don't have to have the same rules in every single place, which on the more forgiving parts of the machine, you can keep everybody safe, but you can also maximize productivity. So that's pretty important as well. Next slide. And the other thing that, as we're getting back to the network system thing, the key thing here is that when you've got everything networked, again, over an industrial Ethernet, then you've got super fast response. In fact, these systems are safer than hardwired systems. Early on, there was a whole nervousness about doing Ethernet versus, something hardwired, but you're going to get so much better performance. I mean, 5 times faster, that's a huge difference in how quickly the system can respond. And that's important because depending on where you're at in the system, you've got spool and spool going on, and it's got some inertia going. It doesn't matter if you cut the power. that baby's going to keep rolling unless it's got a lockdown. So that's where that kind of a fast response makes an extremely important difference. Let's see, next slide. Another really important, really exciting thing going on is operations. There is, kind of the old way of handling that was, for things like OEE, right? Everybody wants to get the most out of their equipment. You want to have high availability. You want to be producing as much as possible out of your potential to produce, and you want to have the highest quality or acceptable quality material coming off, and those are kind of the things that feed into OEE. But the way you used to have to look into that and monitor how your systems and your plant floor was doing is gather a bunch of data, and then you'd have to take it offline and analyze it. And in a lot of cases, the data that you were getting was not particularly detailed. It was, is it running? Is it statistically within the parameters that it ought to be? Data collection, a lot of time was sneakernet. You had, maintenance techs running around with data loggers, gathering vibration information, and then everything had to go out to a computer system, and people went through analysis. And it's not to say that the information wasn't useful. It was, but the problem is by the time it got analyzed, there was latency there, and then if we're getting back to the model where there's regularly scheduled downtime, that could be a day, a week, a month, a quarter after the analysis was done. Now you did have people at plants kind of looking to see how the overall utilization level was going on for the machines, but the information was really not as useful and not as effective. And certainly from a maintenance standpoint, if you found something important and it took days or a week to figure out what was going on, and then you weren't going to get a chance to fix it for a month or more, and meanwhile your machine is just merely continuing to have its issues. So not an ideal situation. Next slide, please. So the lovely part about doing these network systems now with the smart components and integrated components is you can get all of that information dang skippy. You can get it in real time. And now you've got your availability, your performance, your quality information. You can get details, not just is it on and is it running within parameters. You can find out, your heat capacity, your loading curve, number of times it's cycled. And the really nice part is this doesn't just give you information. At this point, you start empowering your operators to make changes and make a difference in the performance and operation of the system, because if they can look in real time and see the performance data of their machine, they can adjust idle time. They can figure out if they need to do anything different with changeover time. Do they need to speed up in-feed? Do they need to alter scheduling? I mean, you can get to the point where one operator, on a different shift is, comparing notes with another one to figure out how they got the performance that they did, because it's happening so quickly. It's not like you can say, hey, Joe, what did you do 2 months ago to have that really great day? It can happen right now. So that is really key. Next slide. And the other thing is in terms of condition, again, you're enabling your operators here. They can keep an eye out for imbalances, vibration modes, things that are indicating that you might have bearing failure, that there's an issue with the machine. In some cases, vendors are starting to develop automated tools that can address that. And again, you get faster response. Now you're getting less wear because you see a problem, you're able to take care of it. You don't have that latency that you've had for so long. So that's huge. Next slide. So now we're going to talk about vibrational loop. Most machines have a single frequency that's kind of their natural resonance or harmonic of the machine. But then you also have a whole lot of other frequencies, and that's driven axis by axis. It's got to do with the load. It's got to do with the conditions on a given axis. And it's not just a static thing. I mean, if you've got, I don't know, a palletizer that is picking up a full pallet and moving it from point A to point B and then going back empty, you're going to have a real different set of conditions before and after that. You're going to have different load, different vibrations. Ideally, you want your drive to respond to that. Next slide. So, in some of these cases, with things like trying to decrease settling time with some of these responses, you used to have sort of, well, we'll do a trapezoidal curve, we'll do an S-curve. More recently, there's been some work with observer control where you're trying to be much more careful about these kind of things. And this is where things, as far as I'm concerned, really start getting interesting with this technology, because now you've got systems that can keep an eye on what's happening with vibration, and they can work out ways to keep from exciting the vibration. And they can do it on axis-by-axis basis because you've got the intelligence, you've got the memory, the processing power to do that. So all of a sudden you're being proactive. You're not just trying to work around the vibration, you're trying to avoid creating the vibration. And as you can see in this picture, the one on the bottom doesn't have that correction, the one on the top does. And look at the difference. But this actually goes to another level. You can not just keep from creating vibration, you can actually use your drive to damp the vibration so that you're not just doing no harm, you're actually canceling out, which is absolutely enormous. In one application, they got 10 to 50%, 50% higher throughput by minimizing slosh. Because if you've got too much slosh, then you can't move as quickly. If you move quickly and you've got a lot of ringing or slosh, then what's the point of moving quickly if you're throwing product all over? Similar when you're looking at cranes or gantries or robot arms, and that's not just at dock side and port side and factory kind of things, although servo motors certainly have a role to play there, but also in more compact applications, pick and place, assembly, material transfer, semiconductor wafer handling. You can get 20 to 40% improvement with these kinds of techniques, and that adds up to 30 to 45 additional picks per minute. Now we're talking about some serious firepower here. So again, that's the kind of stuff that you can do with these integrated systems when you have the integrated components, the intelligence, you're networking together, and you're looking at it from a systems level. And the key thing to me here is this kind of stuff is not something that's kind of, we're doing it at a test level and it'll be out in 10 years. This stuff is out there today. Let's see, next slide. Somehow or other I managed to duplicate a slide. My apologies. So next one. There we go. So as far as other things that you can get today, power-saving drives. You've actually got drives out there that are able to close the loop. They can keep track of the load and their situation, so they can determine whether they're sitting idle. You know, if you've commissioned a machine and maybe there are aspects of the motion of the process that you hadn't taken into account, the drive itself can actually make an evaluation and then change its operation in order to address that, to minimize the amount of energy that is and power that it's consuming. If your load is changing, and again, that gets back to that palletizer we were talking about earlier, or maybe you're changing over SKUs and you've got a different weight. I mean, one of the things that I hear a lot is, you know, there used to be machines going 24/7 only producing, you know, 8-ounce bottles of a soft drink or something. And these days, everybody wants just-in-time manufacturing, which is great, but that means that your system really needs to be responsive, and certainly motion control is part of what allows that to happen. But if you've got smart drives or power-saving drives in the loop, then they can help ensure that you're taking advantage of every opportunity for savings. So you've actually got a smart drive that's not just smart enough to do some path planning. It's way out ahead of you, making sure that you're saving power. Let's see, next slide. And the levels of integration get even bigger as far as looking at a line. If you've got your smart components, you've got your smart modules, your smart machine, and it's connected to your line, and it's all running on industrial Ethernet, suddenly you've got all of these sections communicating. So you get a jam. I mean, obviously, we've talked ad nauseum about safety, helping you address that with safe jog and all that sort of thing. But with this level of integration, what you can also do is have the line communicate within itself, so that instead of, you know, oh, we've got a fault, shut down the line, everything stops, and you have to get things back going. And as you probably know, that is not always an easy trick. A lot of times you've got to do a lot of rehoming and really put some time and attention into getting everything up and running. But with these kind of systems, what you can actually do is communicate. So if you have a jam somewhere in the middle, and, you know, I don't know, you've got a converting line, and you've got an arm, you know, loading flat, so you slow it down. You slow down upstream where it's palletizing. You clear the jam where you're erecting, and then the line can go back to full speed. You don't, I mean, buffers are great, but buffers fill up. So this is a way to just kind of nudge everything a little bit slower until you're ready to rock and roll, and then you're going again without overflowing buffers onto the floor and that sort of thing. And the upside there is, you know, you get local peaks and valleys, but you don't have full stoppages. You don't necessarily need to use extra time for rehoming at startup, and you're maximizing your OEE, and everybody's happy. Let's see, next. Another interesting thing going on is auto-tuning, and this is sort of a today and sort of a here in the near term kind of thing. Probably heard about auto-tuning servos. I mean, you know, back in the day, you'd put them in place, and then you've got to crawl out and tune your PID loops and turn pots and get everything up and running, which can be a really time-consuming and annoying process. But today you can get auto-tuning servos from a number of locations for when you're installing things on a machine, kind of thing, when you're commissioning and so on. But that's all, again, with this theme of integration and intelligence, that's all going to the next level now, so that you're going to have auto-tuning capabilities that can adjust to a changing load. At this point, it's not something that's dynamic quite in real time. It's more something that if you change a part number or you've got a major change, if some part of your mechanical system has lost its preload and suddenly your vibration modes are changing, first of all, your intelligent system is now going to tell you that. So you're going to know about it, and then you can run your auto-tuning routine, and boom, it's taken care of, and you're back up running at peak capabilities. And compare that to just kind of having to live with it. And I have not been told this directly, but I wouldn't be shocked if that sort of thing turned into an ongoing, somewhere down the line, who knows when. But that kind of capability, so that you can really keep that optimum performance in your servos going forward. But like I say, that's my guess. That's not anything that anybody has told me. Let me see. And then with all of this that we've been talking about, that's kind of where the technology is today. But as anybody probably with a pulse, at least in the technical area, knows, the Internet of Things is kind of bearing down upon us. Now, what I have read is that the Internet of Things in the consumer space is going to be completely dwarfed by the industrial Internet of Things, because that amount of sensors and intelligent components is just massive in there. And when you look at just the sheer number of sensors and then the facility sensors and all of the components, having all of those communicating is going to bring even greater levels of capability. In fact, there's talk in some quarters about the Industrial Revolution 4.0 being upon us, precisely because of this level of communication and connectivity. So look for much more in the ongoing themes we've been talking about here. Something to keep in mind, too, a lot of this, depending on your background and the skill set of you and your tech folks, could sound a little intimidating, but a lot of the vendors out there are really working hard to make all of this very user-friendly, even automated. So it's pretty accessible stuff out there, and it definitely is something you want to be looking at. Next slide. Of course, one thing that does come up again and again with these kinds of discussions is cost. Obviously, the more capabilities you get in a component, the more it's likely to cost. But cost is a little bit of a squirrely question, because there is the cost of acquisition. There's also operating cost. And most equipment, at least the electronics, I mean the machine itself, is likely to last 30 to 50 years. But certainly the components are going to go at least 10, the electronics. And it's interesting because there seems to be a little bit of a disconnect in how all of this stuff is specified and paid for, because you've got the people who are specifying the new machine, and they've got kind of their wish list, and at the same time they need to get somebody to give approval, so they're trying to minimize it. You've got a plant VP or whatever who's got a certain capital equipment budget, and they're interested in sticking with that, but a totally different budget, totally different person is the operations manager or the plant floor manager. That's, or not plant floor manager, but the plant services manager. That's the person who's writing the hefty checks for power and energy, all the maintenance stuff. And the challenge we've got going here a little bit is the disconnect. It's in the interest of the enterprise to look at these technologies, because overall you're going to make more product and it's going to cost you less to do it with these intelligent components. And long term, pretty much any asset, and this ranges from computer to automation and machinery, TCO dwarfs TCA. The long-term bills that you're paying are always going to be more, but the question is how to make sure that the enterprise as a whole is aware of this. So, just something to keep in mind is look at the big picture and look at all the numbers, because increasingly companies are starting to pay attention to this and kind of get past that silo mentality. Anyway, so I think we have come to the end of our little ride here. Again, integration going on at a number of levels. You get a lot of improvement. And the key thing to me here is it's the integrated components enable it all, and then the higher levels of integration enabled by industrial Ethernet capabilities, that kind of is what lets it go to the next level. So it's worth checking out. There's some pretty exciting stuff going on, and in particular, there's a lot of this that is available today. We're not talking pie in the sky. We're talking call up your vendor. So exciting stuff. And I think we are out of time. So I think, Carrie, this probably goes over to you. Feel free, if you have any questions, feel free to email me, call me, whatever. I am always happy to help. And thank you, by the way, again to our sponsor for sponsoring the workshop, and thank you for attending.
Thanks, Kristen. That was a great presentation. And again, thank you to everyone for participating today, and Micro E-Systems for sponsoring the webinar. I just want to remind everyone that this webinar has been recorded, and an email with a link to the recording will be sent to you in the next 24 hours. If you have any questions on the presentation material, please feel free to email Kristen or myself. And as always, visit motioncontrolonline.org for a list of our upcoming webinars. Our next webcast is Wednesday, November 12th, and that one is titled Machine Maintenance, Learn Easy Ways to Make Your Machine Last Longer. Thank you, and hope you have a great day.